Okay, today we're looking at ray diagrams for mirrors. Just a quick review of a few terms. A ray is a single beam of light traveling in a straight line. So we can create what we're going to call ray diagrams to figure out where an image is formed in a mirror and also as we get into lenses. So a virtual image by definition is any image that appears to be behind the mirror. It cannot appear on a screen. Converse to that is a real image. A real image is where light emanates from and can be formed on a screen. A movie image is a real screen. Think about the images as you get into lenses. Lenses, you can form the image again on a screen. An incident ray, incident think incoming, so it's a light ray that is coming in and strikes the surface. A reflected ray then is any ray that then bounces off that mirror. If we take a look at a plane mirror in terms of ray diagram, we're going to look at light rays that are emanating off of any one point. So if we start by looking at the arrowhead, light's going to go off in all directions, but we're just going to take and focus on a couple of light rays. So one, a light ray that comes off of the top and hits straight to the mirror. The incident ray hits the mirror and then bounces back normal, so incident's going one way and it reflects straight back off of that. If we then take the bottom part of the arrowhead and project that up, it will hit the mirror. There's the incident ray, and then the reflected ray again will go back up that way. So if our eyes are up here viewing our feet, here is the incident ray, here is the reflected ray. The angle of incidence equals the angle of reflection, so theta I equals the theta r. So here is the incident angle, and there is the reflected angle in here. And this is the normal. Where the reflected rays appear to cross is where the image is reformed. So here, if we take and project that back, and then we also look at the feet. The feet sort of come in and do just like the arrowhead, bouncing back, and where those two lines cross, there's our image formed. So if we project this back, our image is formed right there. So here is the arrowhead, here is the tail, there's your image. By definition, this is going to be our image distance off of the mirror, and this is going to be our object distance. We could also look at that if we look at, say, here's our eye, looking at this image. A light ray that comes off of the arrowhead will reflect back. Again, angle of incidence equals angle of reflection, so with the normal. If we then take a look at a light ray that comes off of our feet, it will hit the mirror and bounce back again up towards our eye. Again, this reflected angle and this incident angle are the same. If we follow that ray back, follow this ray back, and then take a look at that light ray that's going parallel, and where they cross, our image is formed again. So again, d-object, d-image, and wherever we look, the object distance and the image distance will always be the same. So on a flat mirror, DO is equal to DI. To DI. And we're going to define magnification as the height of the image over the height of the object. And we're going to see also that that's equal to a negative DI over DO. So we'll hold on to those. We'll look at those a little bit later. Okay, so let's take a look now at a concave mirror. And we look at a concave, remember that is caved in. And a couple of terms we need to look at here is that one, if this is the center of curvature of the mirror, so if you take a compass and strike out that curve, this would be the center of curvature, so that this is our radius. Radius r, and our focal point here, F, is where all the light rays, parallel light rays, will appear to converge. So F, distance F to the mirror, is equal to the radius divided by 2. So again, if we take a look at all the parallel light rays coming in, if this is our focus point down here, and we look at a parallel light ray coming in, it will reflect through the focus. Take another parallel light ray again, it'll reflect back through the focus. So really, any light ray hitting that mirror that's parallel to that axis of symmetry will reflect back through. Okay, so let's take and form an image now. So here is our focal point. Here's our center of curvature. And we could take any 3 lines to sort of create our image. So let's put our object back here for starters. So here's our object. And again, our distance to the mirror is going to be here. This is DO. So any light ray that goes parallel to our axis will reflect and go through our focal point. And any light ray that goes through our focal point reflects parallel. So our image is formed right there. There's our image. And we can describe that image using 3 terms. One, it's either real or virtual. Since the object and the image are on the same side, it is going to be a real image. It is upside down, and we call that inverted. And then we describe the size. Is it bigger, smaller, or the same size? And here we can sort of see that it is smaller also. Okay, so any distant object, you'll sort of get that kind of thing. Let's take a look at another example. What happens if we get real close to the mirror and something neat happens here? So let's say we're actually between the focus and the mirror. So we put our object here. This is our object. So we take a light ray that is parallel. So parallel to the surface will reflect back through the focus. And then if we take a light ray that's as if it comes off the focus point, it will reflect parallel. And you can see those 2 light rays do not cross each other, but if you project them backwards, where the 2 reflected rays cross again will reform the image. Again, make sure you keep redrawing the image. Don't just make the lines and say there it is. So here's our image, and now notice it's now behind the mirror. So this is a virtual. It's larger, and it's upright. If you take and draw the object, the object was actually standing right at the focal point, something really interesting happens where the image doesn't form anywhere. None of the reflected rays cross each other. They all reflect parallel. So no image is formed. You should take and do that for yourself. So that's the concave mirror. Let's take a look at a convex mirror, which is just the other side of this concave. So here's a convex mirror. Again, here's our focal point. Here's our center of curvature. And any light ray that comes in parallel will reflect as if it came from the focus. So any light ray that's parallel reflects as if it came from the focus point and reflects like that. So there's the incoming ray, reflected rays. So how do we now do this one? And you see these types of mirrors in all kinds of places. Your side view mirrors sometimes have them, trucks, stores. It gives you a nice broad view of everything. So let's take a look at the images that are formed here. So again, here's our focal point, here's our center of curvature, and let's put our object out here. Again, take a light ray that is parallel. So here is a parallel to the axis, and then we take and reflect that as if it came from the focus. Here we can't really go through, the light ray doesn't go through the focus, but we can go towards the focus. So as we go towards the focus, once we hit the mirror, we will reflect back parallel. Again, these 2 rays won't cross, but if we project them backwards, this point right here is where the 2 reflected rays appear to cross, and that is where our image will be formed right there. And then we can describe that image. It's smaller, it's upright, and because it's behind the mirror, it is virtual. And those are the three descriptors that we'll use. So here, it doesn't matter where that object is. It can be near or far away, but you will always get the smaller, upright, and virtual image with a convex mirror. So you'll never get a real image with a convex mirror.